So the problem here asks us to determine the center of mass of the metal bracket. And it says it has uniform density and thickness, which helps us, right? So by thickness, we mean how far into the page it goes, right? So like this, we know that it's a uniform thickness throughout the entire thing. We don't care what that thickness is right now because it is uniform. Okay, but that's what the metal bracket looks like, and we can call that thickness T, but it doesn't actually matter for us right now. We can then recognize here that it says it's also a uniform density, right? And that helps us because we're going to have to think about how do we find mass if we have a solid object. So we have to relate mass, density, and volume. So we can start by saying, first of all, that density, right, is going to be the total mass over the total volume. So for all of these parts, when we go to put the mass in, we can say that the mass is equal to the density times the volume. So we use that formula several times through, and we can say for now that we don't know what the density is, but we can call it rho. Okay, this symbol here for density, okay, rho, the Greek symbol. Now, since they have uniform density and thickness throughout, what we could really do here is think of this as three different pieces, and each of these pieces has its own symmetry involved. So I'm going to go ahead and put dotted lines here and here. Okay, and we're going to say that this is the center of mass of the first one, of the second one, and of the third one. And I can do that because of the fact that we're looking at a metal bracket and these are rectangles here. So the center of mass of a rectangle will be the center of that rectangle, horizontally and vertically. So this gives us an idea of where we can concentrate our mass to simplify the formula. So let's find those locations to start. So I need to first think about location-wise, where is my origin? So I'm going to overwrite in red here, and I'm going to say that I'm going to call this my y-axis here, running along the vertical length there. And I'm going to say that this is my x-axis here. Okay. And again, we have, the solid here still. Don't forget, it's still here. So let me maybe go back over that a little bit with this black marker, so we can see that it's still there. But that's our xy axis that we're going to use, and we're going to measure everything based off the xy axis here. So let's call this object A, let's call this object B, and object C, just for naming purposes. And let's list the center of mass values. So object A, B, and C are each going to have an x and a y value for their center of mass. And what we're doing is simply just finding the midpoints, right? So for object A, it's going to be half of the 0.15, so it should be 0.075. And that's going to be the x value. Okay, and that's CoM, by the way. This is not centimeters here. This just says center of mass, center of mass. We're measuring everything in meters, okay? All the dimensions were given in meters. Oh, this one's not given in meters. That should be given in meters. Then we want to go ahead and take a look at the y value. Well, the y value is not going to be half of this. Be careful, right? This one we only needed to go halfway across the 0.15. This is 0.95 plus this additional height of 0.2. So 0.95 plus 0.2, and then divided by 2, 0.575. For part B, we know that we're going to go halfway across here, but we also want already 0.15. So half of 0.75, that's this distance here of 0.375 plus 0.15. I'm going to get 0.525. Oops. And then for the y value for this one, let's see, for the y value, we're going to go all the way up here, 0.95 meters, and then halfway up this, which is another 0.1. So 0.95 plus 0.1, so 1.05. And finally, part C, we're going to have to go over 0.15, another 0.75, and then this far over to get to point C. So 0.09. So we've got 0.15 plus 0.75 plus 0.09, which is 0.99. And then last, we need the y value there. So let's figure that out. We're going to go up 0.95 meters Then we're going to come back down a little bit. Let's think. Let's go up the full way instead to here. And then let's come back down 0.3, right? This would be coming back down to the middle because this whole thing is 0.6. So coming back down 0.3. So the 0.95 plus the 0.2, or I mean, I guess we could just subtract the 0.1 from that. So 0.85 is what we'll get. But what I was saying was really 0.95 plus 0.2 is 1.05. And then we're up here, and 1.05 minus 0.3 is going to give us 0.85. So those are our center of masses, and we're going to need those values to calculate the overall center of mass of this shape. Now, interestingly enough, ask yourself, and maybe pause the video after I ask this question, where will the center of mass end up being? Or where do you think it'll be? Like, you know, will it be here, 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 somewhere along the first member, the second, the third, somewhere in here, over here? Like, think logically of where it might end up being. Now that we've got our center of masses for each of these objects listed, we should now calculate the actual mass of each of these objects. So I'm going to extend this table a little bit. I'm going to add a column for the mass. Okay, and we have to remind ourselves that the mass, in this case, is going to equal the density times the volume. I know we don't know density, it's fine, we'll leave it as rho, and we don't know the thickness, so we're calling that T. But the rest of the dimensions we do know. So for object A, I want to consider the fact that, again, this goes up 0.95 plus another 0.2. Okay, so that's going to be 1.15 is going to be the height. The width is 0.15. Zoom out a little bit. The thickness or depth is T, and again the density is rho. So that's the volume right there. That's height times width times thickness times the density rho. The second one we'll take a look at is going to be a width of 0.75. We see that already. A height of 0.2. A thickness T and a density rho. And then finally the last one there is going to be 0.6 as a height, 0.18 as a width, T as a thickness, and density as rho. So we'll see the thickness and rho in all of these. So had this problem involved 3 different materials, you would just change the density value for each of them in the next part. Again, we don't know what the density is, but since it's uniform, we don't care. It will obviously cancel out. But if this had been one material, like steel, and then aluminum, and then zinc, you might want to consider the fact that you have different densities, and that's where those go. If also there are different thicknesses, then we'd have to think about the thickness as well. And that would have to then, we'd have to deal with a third dimension for center of mass. Okay, we're assuming that the center of mass for this object, wherever it turns out, will be halfway between here and here, right? So 1/2 T into the page is where it will be, okay, just as an average value, because we know it's the same thickness throughout the whole thing. So now that we've got all these values, let's go ahead and write our formulas. I'm going to zoom out a little bit and move this over. And we want to think about the formula for the center of mass in the x and the y direction. So let's start with the x center of mass formula. And for this, we want to take our mass of each individual item times its center of mass. So the mass of object A times the center of mass of object A plus the mass of object B times the center of mass of object B plus the mass of object C times the center of mass, all over the total mass. For now, let's say, I'll put this up here. Let M equal M1 plus M2 plus M3. Or A, B, and C, sorry. A, B, and C. And then the y center of mass, we have to do the same thing, but let's just work on the x for now. We got a couple things to substitute in here. For the mass of object A, and for all the masses, before I plug all this in and do a lot of work, what I'm going to notice is that if I get the total mass, which I can do by summing together what? These 3 entries right here. So let me write the numbers on the side. 1.15 times 0.15. That's going to yield 0.1725. And that'll be, again, a thickness times density. 0.75 times 0.2. That'll be 15, that makes sense, out of 75. And then 0.6 times 0.18, 0.108. So when I sum these three values together, 0.108 plus 0.15 plus 0.1725, I'll yield 0.4305. I'll put it up here. 0.4305. And that's the total mass, again, times the thickness times the density, right? Times the thickness times the density. So that's my point I'm trying to make here, actually. All of these masses are multiplied by thickness and density. So if I think about it, I'm going to have here, for the mass of object A, this number, which has thickness density. Here, thickness density. Here, thickness density. And then finally here, I'll have this number times the thickness times the density. So these are all going to cancel. So I'm going to cancel them right now and just not include them. Okay, so inherently, what are we really looking at in this problem? We're really just looking at the area of this, right? That's what the area is right here. The area of this, which is here, and the area of this guy, which is right here. And then the total mass becomes the total entire area, which is this number right here. Again, that's because the thickness is uniform and the density is uniform as well. So I've got 0.1725 times the x value, the center of mass, which is 0.075, plus, I'm going to run out of room clearly, 0.15 times the x center of mass, 0.525. Go ahead and just give myself a little more room. Of course I can right now. Plus the third mass, 0.108. And let me zoom out a little bit. I gotta stop including zeros. 0.108 times the x center of mass for object C, which is 0.99. And that's all divided by the total mass, 0.4305. Okay? We get an answer of 0.46 meters. So let's estimate where that is along the x-axis, right? The x center of mass. So this is 0.15 and this is 0.75. So together this is going to be 0.9 to here. So it's about halfway to there. So we're here on the x-axis. It means our center of mass lies somewhere along this line. The line x equals 0.46. Okay, which probably makes sense, right? I didn't expect it to be right in the middle here because there's more mass over here than there is over here. So I expected it to be kind of slanted, or not slanted, but skewed to the left here, skewed. Now I'm going to do the same thing with the y center of mass, a little bit quicker here though. And we get an answer of 0.81 meters. Let's go ahead and zoom in a little bit to see this. So 0.46, 0.81. 0.46, again, as we said, like around here. Then 0.81, so 0.95 would be to here, so we're talking 0.15 below that, so about right here. Okay, so here's our center of mass, and that's to be expected. Again, it should have been not at the center of A, because here, look, if it was somewhere along this line, it can't be. We have way more mass up here. We have very little mass below this line, so we know it's going to be shifted above the midline of this, and we know it's going to be shifted to the left of this midline. So this would have been, if it was an even perfect rectangle, would have been right here. So it was shifted up because there's more mass up here, and then it was shifted left because there's more mass down here. Okay, so we're in this range somewhere. Feel free to try this kind of a problem again and just make it a bit tougher on yourself if you want to. You can make the shapes a bit tougher, you can change the density, change the thickness, make something that changes thickness as a function of the length of it if you want to. But feel free to explore that idea.